the light that wakes you each morning is a ghost. By the time it spills across your pillow, it has already traveled 93 million miles, leaving the sun more than 8 minutes ago. What feels like now is in fact history arriving late. Look closer and the illusion deepens. The moon in the night sky, you see it as it was 1.3 seconds ago. The stars overhead, they may have died thousands of years before their light finally reached your eyes. Even this very page is not truly here in the present. Light reflecting from it takes fractions of a second to reach you. The truth is unsettling yet beautiful. You have never lived in the present. Every sight, every sound, every touch belongs to the past. What you call reality is a seamless story your brain assembles from delays. And that story is your only way of knowing the universe. You wake up to light pouring through your window. The light looks like a simple thing. It feels like now. But that light began its trip over 8 minutes ago. When you open your eyes, the sun you see has already sent its beam across space and time. You are looking at the sun as it was 8 minutes and 19 seconds before. The reason is the speed of light. Light moves at a fixed and very large speed in empty space. Scientists set the number with great care. The value is 299,792,458 meters per second. That long number tells us that light can cross vast distances very fast. It is fast enough to circle the Earth many times in a second. But it is not instant, and that simple fact changes everything we see. Because light takes time to travel, we always see things as they were in the past. The sun is very far from us, about 93 million miles away. That is why the sunlight we feel on a morning face started its journey more than 8 minutes earlier. When you trace that light backward, you are tracing the sun in its earlier state. The same is true for the moon and for every star and galaxy in the sky. Even things that look very close are already history by the time their light reaches you. The moon hangs like a coin in the night, but the light from the moon left about 1.3 seconds before it reaches your eye. If someone on the moon waved a hand, you would see that wave a little more than a second after it happened. A cup on your table sends its light to your eye in much less time, but still in a time that physics can measure. Those tiny delays are small, but real. Think for a moment about the view outside your window. The car on the street, the bird in the tree, the cloud moving over the roof are all slightly older than the moment you notice them. Your living room is a patchwork of tiny times dot. The lamp in the wall and the page of a book are all showing versions of the recent past. The farther something is, the older the picture becomes. This is why the Andromeda galaxy shines to us with light that left it 2.5 million years ago. When astronomers point a powerful telescope at Andromeda, they are reading a scene from 2.5 million years before, a picture of that galaxy as it once was. A light year is simply the distance light travels in 1 year. It is a large unit because space is large. If a star is 100 light years away, the light we see left 100 years ago. That means when you look up at a distant star, you are looking into its past. Sometimes the gap is small and close to our daily life. Sometimes the gap is so vast that the light you see began its trip before human stories began. This strange fact is worth sitting with, because it quietly rearranges how we think about presence. We like to imagine the present as a thin line that moves from future to past. But what our eyes and instruments deliver are many lines stacked and blended. The brain must reach into its store of skills to line them up into a single scene so that you can reach, step, and speak without tripping over delay. The brain smooths and fills, and sometimes it guesses to make the world feel continuous. To feel what I mean, imagine a movie that runs just a few frames behind the action. The movie seems right enough to catch a thrown ball or to clap hands in time with music. Yet it is still an edited version. Your mind fills gaps, so you hardly notice the editing. That craft of filling and guessing is why life feels immediate even though it is made of past light. The present you live in is a calm story sewn from many old moments. There is another gentle surprise. Some of the points of light you spot on a very clear night might be the sign of a star that is no longer burning. Because light takes time to travel, there are places in the sky that show events from ages past. A huge explosion in a far galaxy may have happened millions or billions of years ago, and yet its glow might only be reaching us now. Scientists often call telescopes time machines because they let us read this slow record of the cosmos and see events long gone. At the same time, do not lose the everyday feeling that most stars and near objects are still very much alive. Stars live for millions and billions of years. The points you can see with your own eyes are often close enough and long-lived enough that they remain as you remember them. The odd chance that a particular distant star has already died does not make the night sky a graveyard. It simply means the sky contains both living lights and ancient stories. The reason this matters is not just for wonder. It matters because our sense of now is a work of the mind. It matters for how we plan and how we trust our senses. It matters for science and for our quiet, small acts. When a doctor watches changing light in a scan, they know the signal is delayed. When an engineer sends a message to a probe far away, they must count minutes or hours for a reply. When you look up at a clear sky, you are reading pages of a great book written in light. This knowledge also changes our language of time. We speak of the present and the past as if they had clear borders. But sight teaches us that the present is porous. What we hold as the now is a careful mix of very near memories and faraway stories. That feeling can be gentle and freeing. It can also be humbling. We stand on a small planet that reads the past, and we are able to learn more because of that delay. Imagine waking up and blinking toward the window as sunlight pours in. It feels immediate, warm, and true. Yet, that light began its journey more than a few minutes before you opened your eyes. The truth is gentle and strange. Your body and brain are not instant machines. They listen and feel and see with a slow, careful lag. The eye gathers light, nerves carry signals, and the brain stitches everything together. That stitching takes time. The first piece of this story is that the brain needs a moment to turn raw light into what you call seeing. It is not unusual for the visual system to need roughly 1/10 of a second to process the flow of images from the eye into useful information that guides action. This gap is small but real, and life has learned to live with it. If you reach toward a cup on a table, your hand does not simply act on a live snapshot. The eye sends a stream of changing light into the brain. The brain begins by detecting simple things like edges and contrasts. Then it sorts out color and motion. Later it recognizes bigger shapes and finally identifies the object as a cup. These steps do not all happen at once. They are like an assembly line where different stations do different jobs. Some stations work faster and some take longer. The effect is that the picture you feel you are seeing now is actually made of several slightly older parts combined so they match. Some bits are fresher, some bits are a little older, but the mind blends them so the world looks calm and smooth. Sound follows its own clock. A voice across a room reaches your ear almost instantly in human terms, but the brain still needs time to sort the pattern of air pressure into meaning. Parts of the auditory system respond in myriadozen of milliseconds, and the brain then spends more time integrating and making sense of what was heard. Listening to speech or music depends on both the quick arrival of sound and the slower work of the brain to fold the sound into words and rhythm. Because sight and hearing run on different schedules, the brain must find ways to line them up so a spoken word appears to match a moving mouth or a struck drum. Touch brings another variety of timing. Some nerve fibers that signal touch and pressure carry messages very fast. Others that carry slower feelings like warmth or dull pain are much slower. The speed at which these signals run along your nerves can vary by 10 or even 100 times. That is why a light tap on the skin feels like a quick note, while a slow ache takes its time to register. Your whole sense of contact is built from many different speeds of travel, and the brain learns to expect and correct for those differences so you do not feel disjointed. If you step back and look at these layers together, you see why people sometimes say the body is a time delay machine. The brain faces signals that arrive at different paces. One choice the brain often makes is to wait a tiny amount of time so that the slowest voice in the group can arrive. This is not laziness. It is a sensible rule that prevents confusion. If the brain tried to act on the fastest signal alone, it would end up with a jumble when the other inputs finally arrived. Instead, the brain holds a brief moment and then blends what came a little earlier and what came a little later into a single smooth scene you call now. This practice of small waits and careful blending is what lets you catch a ball or talk and listen without falling apart. This slow blending and clever guessing are also why certain illusions are possible. In a well-known experiment, a person can be made to feel that a fake hand belongs to their body when the sight of that hand being touched is perfectly timed with the touch on their real hand. If the timing is off by too much, the illusion fails. The brain is sensitive to how close in time different signals are, and it binds them into single events only within a certain window dot. If sight and touch fall inside that window, they become one felt thing. If they do not, the brain keeps them apart. This temporal window is one of the ways the brain decides which pieces to glue together into the experience you trust as your body. There is also a quieter, wider time trick that helps the world feel steady. The brain does not try to show you every tiny change as it happens. That would be dizzying. Instead, for some kinds of vision, the brain smooths what it sees by blending in what happened in the recent past. Scientific work has shown that perception can be pulled toward things seen up to many seconds before, so that an object that is slowly changing can look more constant than it really is. In a way, your mind keeps a short-running story of the last moments and reads the present from that story instead of from a single instant. That is part of how a busy, noisy scene becomes calm, so you can walk and talk without distraction. All of this adds to a simple answer for a big question. If your brain is always a little behind, how do you function as if you are right on time? The answer is that your body and brain work together with delays, prediction, and smart binding to make life smooth. They accept the delays, they learn the patterns of the world, and they constantly guess what will come next. When the guesses are good, we feel seamless. When they fail, we notice odd moments where time seems stretched or the world seems to slip. But most of the time, the design is so well tuned that you do not think about it at all. Imagine you are sitting by a window and watching the world as if it were happening right now. A child drops a toy. A neighbor closes a door. A bird lands on the sill. Everything feels immediate. It feels as if the world hands you a single clean moment and you live inside it. That feeling is warm and comforting, but it is also a gentle trick dot. The present you sense is not a single slice of time handed to you whole. It is a kind of craft put together by the mind from bits that arrived at different times. The brain takes a few pieces, smooths their edges, fills the blanks, and gives you the calm sense of now. Scientists have a name for one of the ways the brain does this. They call it a continuity field. What that idea means in plain terms is this. Your eye and your brain do not treat each instant as brand new and unrelated to what came before. Instead, the brain borrows information from a moment ago to make sense of the moment you're trying to see. If you look at a face and then look away and look back, your brain leans a little on what it remembers from the first glance, so the new glance feels stable. This is not a mistake. It is a way the brain makes the world less jumpy and more predictable. The science shows that what you see now is gently pulled toward what you saw a heartbeat ago. And that pull helps keep images steady when the world or your eyes move. That editing work feels like what a film editor does. The brain is not simply playing a single live feed. It is taking short films from just a few moments back, matching their frames, and joining them so motion looks smooth and objects keep their shapes. To do this, the brain is not only using what it has already sensed, it is also making guesses about what will come next. Modern thinking in brain science talks about the brain as a prediction machine. In this view, the brain builds small models of the world and uses them to expect what the senses will deliver. When the expectation and the incoming signal line up, perception is quick and calm. When they do not, the brain notices the surprise and updates the model. This constant looping of guess and check helps the mind hide small delays and make sense of a messy flow of input. A hard part of this craft is that the different senses do not arrive at the same pace. Light, sound, and touch each travel and are processed with their own clocks. A picture of a moving car may land in your eye at a slightly different time than the sound of its horn reaches your ear. Your sense of touch follows another route with another pace dot. The brain faces a timing puzzle. To solve it, the mind uses a kind of joining window. If two signals from different senses arrive close enough in time, the brain treats them as coming from the same event. If they are too far apart, the brain keeps them separate. This window is flexible. Practice and context can widen or narrow it. People vary in how wide their window is. That flexibility is part of why two friends can clap and sing in the same room and feel in time even when tiny delays are present. The brain simply decides those separate pieces belong together. Prediction plays a second and deeper role beyond simple timing. The brain often prepares the body before a deliberate action even reaches conscious notice. Experiments show that electrical activity in the brain can rise a little before a person feels they have decided to move. That slow build of readiness is one of the reasons philosophers and scientists have long argued about how free will feels. From a practical point of view, the brain is priming the motor system and making a guess about the immediate future so that action can be smooth and timely. That preparation and the mind's guesses together make it possible to act in a way that feels immediate, even though parts of the process started before you became aware of them. All of this editing and predicting creates a present that is not an instant, but a short stretch of time. Many thinkers and experiments point to a span of a few seconds as the window in which our mind weaves experience into a single now. That short stretch is sometimes called the specious present. It is long enough for a short sentence, a single gesture, or a small musical phrase to feel whole. It is also short enough that we still notice one thing coming after another. In this window, the brain keeps a running record of the very recent past and makes an educated guess about what belongs together. The result is a sense of continuity that carries the feeling of being in the moment. When the brain gets its timing right, the world feels seamless. Catching a tossed ball feels natural because the eye, the prediction, and the movement all line up. Two musicians can keep a beat together because each predicts the other's next move and corrects for small delays. The mind is extraordinarily good at this work, but when predictions fail, or when the timing is pushed beyond the brain's window, something odd happens. Time can feel stretched or slowed. People who survive sudden shocks sometimes report that the world seemed to slow down. Scientists think that in such moments the normal predictive machinery is overwhelmed and the brain pays closer attention to the raw flow of events, making memories denser and time feel longer in retrospect. You can also see the limits of the brain's glue in certain illusions. If a sight and a touch are timed just right, the mind will bind them, and you may feel that a false hand is your own. If the touch and the sight are off by too much, the illusion fails. That sensitivity shows that the mind makes careful, not careless decisions about what to bind. The brain uses timing as a kind of trust test. If the pieces are close enough in time, they pass and are joined into one event. If not, the brain keeps them apart. Attention steers all of this. What you focus on narrows the stitching. When you concentrate on a face, you notice small mismatches and the mind tightens its window. When you are relaxed and unfocused, the window may widen and the world feels more blended. People differ in these habits. Some minds hold a short tight now and catch tiny differences. Others let a larger stretch count as now and enjoy a softer, more flowing sense of time. The deeper lesson is gentle and human. Your present is not a raw slice handed down by the world. It is a careful story your brain tells from bits of recent past and smart guesses about the near future. That story is usually so good you do not notice the cut and splice. It allows you to move, to speak, to laugh, and to share time with other people in ways that feel natural. The illusion of now is not a flaw. It is a practical masterpiece that helps you live with delays and uncertainty. Close your eyes for a moment and imagine a small town clock tower. In that town, people look to the tower to know when to work and when to rest. Your brain is a city of such clocks. Some of them tick so fast you do not notice, guiding a single step or the flick of an eye. Others keep a calmer beat, helping you plan your day and sleep at the right hour. None of these clocks are simple gears in a watch. They are networks of cells, rivers of electricity, and pools of chemicals talking to each other. They share information and they correct one another. They let you live fluidly from moment to moment without tripping over tiny delays. When you reach for a cup or catch a ball, the timing required is tiny. These tasks need timing on the order often to hundreds of milliseconds. The brain uses different parts for that work. One of the best-known helpers is the cerebellum. Many people think of the cerebellum as a part that keeps balance and smooth movement, and it is that, but it also plays a key role in timing. The cerebellum helps the brain predict the exact moment a finger will touch a surface or when a sound will arrive. It sends precise timing signals so movements come out clean and on time. When the cerebellum is not working well, the world feels clumsy and timing slips. For tasks that stretch over seconds, the front of the brain takes the lead. The prefrontal cortex helps you hold a plan in mind and decide when to act. When you wait to speak so you do not interrupt, or when you time a pause before turning into traffic, the prefrontal cortex is doing its slow, careful counting. It links short memories with goals and uses that link to shape what you do over seconds and minutes. It is the manager that makes sure small actions fit into a larger plan. Scientists describe its role in controlling action in time and in using memory to judge durations. Far beneath plans and quick moves, there is a very different clock that keeps your day and night steady. Hidden in the middle of the brain, a small region called the suprachiasmatic nucleus makes the body follow the 24-hour cycle of light and dark. This internal day-night timer sets the rhythm for sleep, hunger, body temperature, and many other daily processes. It synchronizes whole systems by reading light at the eyes and telling the rest of the brain and body what time it is. This is why light at the wrong hour can upset sleep, and why travel across time zones can leave you tired until your internal clock resets. These clocks do not act alone. Imagine musicians in an orchestra. Each instrument has its own part and its own pace. The brain coordinates the musicians so a single melody can be played. Millisecond timing helps speech and catching. Second timing helps music and conversation. Minute and hour timing help planning and meeting appointments. The circadian rhythm keeps the stage lighting in tune with the day. When the orchestra is in sync, life flows. When parts fall out of step, the result can be awkward or harmful. Chemistry is the conductor that nudges these clocks along. Dopamine is one of the most important chemicals for time. It affects how fast or slow our inner beat feels. When dopamine levels change, the sense of time can shift. People sometimes say time flies when they are having fun. That feeling links to how reward and dopamine change the inner counting of moments. Scientists have shown that altering dopamine in animals and people can speed up or slow down how they judge short intervals. This helps explain why mood, excitement, and certain drugs make the same minutes feel very different. Other chemicals and the health of neurons also matter. Some brain cells fire in patterns that mark time. These cells can wear out, slow down, or change their rhythm with age, illness, or lack of sleep. Medicines and substances that change brain chemistry can make time feel faster or slower. For example, stimulants can sharpen a sense of urgency, while sedatives can make the world feel heavy and slow. The way these chemicals change timing gives doctors clues about how the systems normally work and how they go wrong. When timing systems wobble, the effects can show up in clear ways. Parkinson's disease is a condition where the systems that use dopamine are damaged. People with Parkinson's often have trouble judging short intervals and coordinating movement in time. Their steps may become slow and uneven because the inner beat that guides action is fuzzy. Attention deficit hyperactivity disorder can make it hard to estimate how long something will take and to keep to a plan. Schizophrenia and some other mental disorders can also change how time is experienced, making sequences feel jumbled or the order of events unclear. Brain injuries and strokes may damage parts of the timing network and leave people unable to sense or act in time the way they used to. Research across many conditions shows that timing is a window into the health of many brain systems. There are gentle ways to work with these clocks. Practice teaches the brain to be more precise. Musicians and athletes refine their timing through long training until anticipation and action match closely. Simple tools like timers and routines help when internal time is unreliable. Sleep and light are powerful allies for circadian health. Medicines can help too when disorders impair timing, but they require careful use because they affect the chemical balance that every clock depends on. The story of timing in the brain also carries a human lesson. Time inside us is not a single steady line. It is a set of linked abilities that together let us act, plan, sleep, and share moments with other people. The same networks that help a violinist hold perfect rhythm let you answer a friend at just the right moment. The same chemicals that make an afternoon exciting also nudge the inner beat so the hours feel shorter. This is why a day can pass in a rush of joy or drag under a cloud of worry. Both are honest experiences created by the very machinery that makes life possible. If you listen to your day, you can notice the clocks at work. There is the quick timing that lets you catch a falling dish dot. There is the softer pulse that keeps a conversation smooth. There is the slow drum that tells you when to sleep and when to wake. All of these clocks meet inside your head, and together they create the feeling of moving through time. They are not perfect, but they are clever. They take messy signals and make them useful. They let you be punctual, playful, thoughtful, and rested. In the quiet of a morning, you might feel the neat order of these systems. The breath, the small movements, the plan for the day are all held by networks counting and predicting and correcting. That is what it means to be a time traveler inside your own body. You are guided by many clocks, and their steady work is the soft, invisible craft that makes living in time feel simple and natural. Imagine walking into a forest at dawn. The trees are a few meters tall, the birds hop from branch to branch, the wind swings leaves at a steady human pace, and your hands can reach the bark. Your senses were built to live in that kind of world. Scientists and thinkers have a name for the idea that every species lives in its own felt world, shaped by what matters to survival. The German word Umwelt captures that truth. A tick smells a warm spot, a bat hears tiny echoes, and a human notices faces and tools. What is real for each species is the information that helps it survive and act, not the whole universe in its raw detail. This is what people mean when they speak of the middle world. It is the Goldilocks zone of everyday life, not too big and not too small. Rocks and trees and animals move at speeds that we can follow with our eyes. Distances are the ones we can walk across or throw things across. Light, sound, and touch come in patterns that fit our bodies and our nervous systems. These patterns shaped how our senses developed and how our brain learned to make meaning out of inputs. The study of sensory ecology shows that organisms build perception systems tuned to capture the kinds of signals that mattered to their lives. In other words, evolution favors perceptions that work well for living in the middle world, not perceptions that describe the whole of reality. Because our senses were honed in this middle world, we develop habits of thought that feel true inside it. We assume that bigger things are stronger, that faster things carry more force, and that two events that look to us like they happened at the same time really did. Those rules are useful when the world is made of trees, animals, and rocks. They are simple, quick rules that let us act without heavy thinking. Our common sense is a toolkit stamped for the scale that mattered to hunter-gatherers and to farmers. It is a brilliant toolkit for many everyday tasks, but it is limited. When we step outside the middle world, that toolkit can lead us astray. The limits show up in small and soft ways and in very large and important ways. Think of how people misread exponential growth. When a virus spreads, a debt compounds, or a technology improves by a fixed percentage, the change can feel slow at first and then suddenly huge. Our minds like straight lines. We tend to make a quick guess by extending a straight line and miss the curve. Economists and psychologists have studied this tendency and found it happens again and again with real consequences for saving, investing, and public health. Underestimating compound change is not a moral failing. It is the product of a brain that evolved to handle people, seasons, and small camps, not long-term compounding and global pandemics. At the very small end of things, the world becomes stranger still. At the scale of atoms and electrons, the rules that helped us survive simply do not apply. Particles can behave like waves. They can seem to be in two places at once until measured. These results are not feelings or tricks of language. They are confirmed by experiments and the mathematical rules of quantum theory. The oddness of the atomic world is not because we lack imagination. It is because natural selection never needed to make us sensible about things that did not affect our ancestors day to day. Quantum mechanics works beautifully for engineers and physicists, but it runs against the grain of the everyday ideas our senses favor. There is also a cost in the way we talk and think. Stories that appeal to immediate harm or to vivid images of danger are easier for the brain to accept than slow-moving threats. Climate change is a good example. The harms unfold over decades and cross whole regions, so they do not fit neatly into the short episodes our minds prefer. Because we discount distant harms, our systems for planning and governing struggle to match the timescales the problem requires. This is not a failing of will. It is the predictable consequence of a brain shaped by seasons and by the need to notice nearby dangers. Recognizing that limitation helps us design routines, institutions, and technologies that guard against our own short sight. There is also a gentle upside. Knowing that our intuition is trained for a narrow slice of reality frees us from trying to make sense of everything by feel alone. It teaches a path to humility. It also points to practical remedies. We can use stories, visuals, and simple tools to stretch our sense of scale. Graphs and simulations can make exponential change feel more real. Timetables and alarms can help manage long-range plans. Schools can teach the habits of thinking that the natural world did not give us. The ancient craft of building instruments and the newer craft of building good public institutions both respond to the same fact. Our middle world is wonderful for living. It is not a full map of what exists. That is fine. We get the best of both worlds when we pair the strengths of our evolved sense with the correcting power of tools and ideas. So the middle world trap is neither a curse nor a condemnation. It is an explanation for why we often trust what feels right and why sometimes reality laughs softly at our confidence. The trick is to learn when feel is enough and when we must reach for instruments, math, and patient thought. When you do that, you keep the gifts of the middle world and gain a clearer view of the very small and very large. You do not abandon the life that your senses make sweet. You simply learn to walk between worlds with care, humility, and the right tools. Close your eyes for a moment and imagine the smallest things you can. Not the things you can hold in your hand, but the tiny bits that make up those things. That tiny world is not like the one you walk through every day. It moves to different drum. It behaves in ways that feel almost like a dream. When you step into that dream, the neat rules you use at a kitchen table stop working. Things are not always where you expect. They do not have definite paths. They seem to be in more than one state at once. This first strangeness is called superposition, and it means that any particle can, in a real way, exist in many possible conditions until something forces it to settle into one. It is not a trick of words. It is what experiments show when we watch very small things closely. The second odd rule is that you cannot know everything about a small thing at once. If you try to pin down exactly where it is, you lose some knowledge about how fast it goes. If you measure its speed very carefully, you blur the exact place. This limit is not a problem with instruments. It is a built-in rule of the microscopic world called the uncertainty principle. It tells us that at the level of atoms, there is a trade-off between knowing where and knowing how fast, and that trade-off is part of how nature is put together. That makes the idea of a single, clear history shaky at the smallest scales, because the usual markers of before and after depend on the object having a clear path through time. If that feels strange, imagine how time itself behaves in that realm. In our daily life, cause comes before effect in attity chain. At the quantum scale, experiments can be arranged to blur that chain so tightly that the idea of a simple before and after seems to fray. Clever physicists have built setups where a choice made after a tiny particle seems to have passed. A place can still change whether it behaved like a wave or like a particle. These delayed choice experiments do not let us send messages to the past, but they do show that our usual way of picturing things moving along and deciding its fate along the way is not always the right picture in the small world. When we study these findings carefully, we see that the laws that govern the very small allow patterns that do not fit into a neat timeline the way our daily stories do. Another way time looks odd at the tiny scale is in a trick called tunneling. Imagine a hill that a small marble could not climb because it does not have enough push. In the quantum world, the marble can sometimes be found on the other side, as if it had slipped through the hill. Particles can cross barriers, even when by the old rules they should not have enough energy to do so. The effect is not magic, but the result of the particle behaving like a wave that reaches through the barrier in a small way. This tunneling is not only a strange thought experiment, it is the reason some kinds of radioactivity happen, and it is the tool behind devices that let us see and work with single atoms. Scientists still argue about how to describe the time spent in the act of tunneling, and that argument shows how strange the quantum clock can be. Perhaps the most eerie feature is something called entanglement. Two tiny things can become linked so that what happens to one seems to echo in the other, even when they are far apart. Change one in the other shows a linked change in a way that cannot be explained by a simple passing of signals through space. Albert Einstein called this spooky action at a distance, and for a long time it felt like an argument against the theory. But careful experiments have shown that the link is real and that entanglement is a dependable resource that physicists can use. It is the backbone of new machines that try to compute and communicate in ways our old devices cannot, and it shows that the small world is woven together in ways our everyday sense of distance does not prepare us for. There is another idea that sounds almost like poetic talk, but it is part of how quantum physics is studied. When particles interact, they often do so by trading what we call virtual particles. These are not little ghosts with their own clocks, but mathematical entities that help us calculate forces. They appear and vanish so quickly that we cannot catch them directly. Still, their brief presence changes how real particles tug and push on one another. In this way, the small world borrows things for a moment and gives them back. And that borrowing can look as if things exist for only an instant or even for a kind of negative time in our equations. The math handles it, and the machines that use these ideas work. But the picture is not one that easily sits with our everyday sense of time. At the heart of the strangeness is a deep puzzle called the measurement problem. The equations of quantum physics give a smooth wave of possible outcomes, yet when we look, we see one clear result. How and when the many possibilities become the single thing we observe is a question that has no single agreed answer. Erwin Schrödinger posed this puzzle in a thought experiment that uses the idea of a cat that might be both alive and not alive until we look. That story is not offered as a real plan, but as a way to show how puzzling the split is between the quantum description and our experience. Different interpretations and different newer ideas try to explain the bridge from many possible pasts to one observed past, but none of them make the problem go away in a way that feels like old common sense. The measurement puzzle is why many physicists choose to rely on careful math rather than mental pictures when they work in this realm. It is important to say what this all does not mean. The quantum world does not give you a clear route to change the past or to perform impossible feats. The odd correlations and quick vanishings obey rules that keep messages from being sent faster than light and keep causal paradoxes from wrecking the everyday world. What the quantum rules do is show that the bedrock of matter and energy does not follow the tidy logic of our common sense. That is why quantum technologies work. They take advantage of these strange rules without breaking the larger ones that keep clocks and cause and effect useful for life. For tasks that need huge numbers of particles, the weirdness averages out and our usual time sense returns. That is the quiet miracle by which the small world makes the big world steady. If you listen to this story with a soft ear, you will hear a subtle lesson. The very small does not obey the neat script of before and after that you learned as a child. It asks for a different language, one of probabilities and waves and links that do not care about distance in the way your hands do. That language is hard to feel. Scientists learn it through math and through patient experiments. The result is a world more strange and more beautiful than our instincts first let us see, and a reminder that the maps in our heads are only a part of the wider country of nature. Even when the rules of atoms and particles bend the idea of time, the everyday clocks that warm your cup and mark your days keep their place, and we are left with two stories to hold together, the small and the familiar. Imagine standing under a night sky and feeling the quiet of distance and time. The stars above look like steady points of light, like friends watching from far away. That feeling is soft and familiar, but the truth behind it is stranger than it first seems. Space and time are woven together in a single cloth called space-time, and when you move through that cloth or when gravity pulls on it, what you call time can stretch and bend. This means that two people in different places or moving in different ways can disagree about what counts as now. The idea is not made up to be confusing. It comes from careful thinking and from experiments that have tested these ideas again and again. One of the first gentle surprises is that time ticks more slowly when you move faster. If you could travel near the speed of light, your clock would lag behind the clocks left at home. The faster you go, the slower your clock appears to outsiders. There is a matching surprise that gravity too can slow time. The deeper you are in a gravity well, the more slowly your seconds pass compared with someone farther away. Both effects are part of the same picture that Albert Einstein gave us more than a century ago. They are not tricks or stories. The slowing of time with speed and with gravity has been seen in many tests and in machines that must account for it to work correctly. Because motion and gravity change how time flows, there cannot be one single shared now that all people everywhere agree on. Two events that seem to happen at the same moment to you might look out of order to someone moving past you on a train or to someone high above the earth. This is the relativity of simultaneity. It means that the simple feeling of a single present moment is a useful idea for our small lives on Earth, but it is not a universal law of the cosmos. Physicists explain this with clear pictures and equations, and those ideas have been tested and found to fit the real world in many ways. The world of everyday tools gives us a gentle, useful example of how strange these ideas can be. The satellites that guide your phone or your car home do not sit still above Earth. They move fast, and they are farther from Earth's gravity than you are. As a result, their clocks tick at a different pace than clocks on the ground. The engineers who run the global positioning system must correct for both the effect of motion and the effect of weaker gravity on the satellites. Without those corrections, your map would be wrong by many meters very quickly. This is a plain and practical place where the bending of time matters to a simple daily task. The same laws also give strange and moving stories about people who travel fast or who live deep in gravity. If you could take a ship that flew near the speed of light to a far star and then came back, your watch might show that only a short while passed for you while decades or centuries passed for those who stayed behind. That thought experiment, often called the twin paradox, is not merely a toy. It follows from the same rules that make GPS work and that are used every day in particle physics and astronomy. The math and the experiments agree that motion and gravity change the pacing of life in a real way. Black holes offer perhaps the most dramatic image. If you watched someone fall toward a black hole from a safe distance, they would seem to slow and slow as they neared the edge called the event horizon. To you, their motions would be stretched out and dimmed until they appeared almost frozen, while their own clock and their own feelings would carry on normally as they crossed the edge. In the language of physics, time near a black hole can be stretched so strongly that, from certain viewpoints, it seems to hang almost still. That fact helps explain why black holes have such strange and powerful effects on light and matter around them. These ideas about time lead naturally to a larger, more ancient question. If space-time is a four-dimensional shape, and all moments are part of that shape, then in some ways, the past and the future are already there in the same way, as places on a map are already there. This picture is often called the block universe or eternalism. It suggests that what we call the present is a slice through a larger reality, and that past and future are equally real in the fabric of space-time. The thought is hard to hold because our inner life feels like a stream that flows, but the block view is one serious way that many physicists and philosophers think about time, and it follows naturally from the simple geometry of the theory of relativity. When you step back from these deep ideas, you see a scale problem that humbles the human mind. The Andromeda galaxy sits at a distance that means its light takes 2.5 million years to reach us. When you look at Andromeda, you are seeing it as it was long before our species existed. The whole sphere of what we can see, the observable universe, stretches across tens of billions of light years. Those numbers are so large they make the span of a human life look like a single breath. The heavens are full of records of long-ago events in distant places, and our senses and our minds are not tuned to live naturally inside those vast stretches of time and space. That mismatch matters for the way we live and think. Our daily sense of time is fine for cooking, for walking, for keeping a promise. It is poor at holding the slow sweep of geological ages or the subtle changes of cosmic expansion. The physics of motion and gravity gives us rules that correct and widen our sense of time. Instruments and careful thought extend the reach of our natural life. Telescopes let us read the light of distant galaxies. Clocks and satellites keep our maps true. And equations help us make sense of what seems strange. In that way, human reason and tools rescue us from the limits of our sense and let us live with the full, large, and beautiful story of the universe. There is a quiet wonder in all this. When you look at the stars, you are seeing old light, and when you check your phone, you are riding on a bed of clocks that must obey the same rules that govern the motion of planets and the pull of black holes. Space swallows time in ways that bend and stretch our sense of what now means, and yet inside that bending, there is room for meaning and choice. Our lives remain real and warm inside a universe that is far larger and stranger than our instincts first let us imagine. That contrast between the small world we live in and the vast cosmos we are part of is not a loss. It is an opening, a place where science and story meet and where the human heart can feel both its smallness and its belonging. Imagine being in a kitchen with a friend and a kettle begins to sing. You do not wait for the steam to tell you the song. Your mind already has a good idea of what will happen next. It expects the hiss to climb and the whistle to sharpen and your hand to reach for the lid. That quiet habit of guessing is not a trick. It is the way the brain lives. Scientists now think of the brain as a prediction machine that is always making small bets about the near future and then checking those bets against what the world actually brings. This idea helps explain why the world feels smooth and why we can act so quickly even though every sense takes time to carry information into the brain. The basic workhorse of the system is simple to picture. The brain builds models that say what it expects to see, hear, or feel. When the senses arrive, the brain measures how different the real input is from its expectation. That difference is a prediction error. If the error is small, the brain will keep its model and go on. If the error is large, the brain will change the model to better fit what happened. Over and over, this loop of guess and check lets the brain learn about the world with very little wasted effort. The loop also explains attention. The brain gives weight to the bits of experience that seem most useful for fixing its mistakes. That means the mind is not a passive recorder. It is always a forward-leaning storyteller that tries to stay one step ahead. This forward-leaning is not only a matter of fancy words. It is the reason a person can catch a ball. The eye sees a moving object in many quick pieces. The brain uses an internal model to simulate the ball's path and predict where the hand should go. The model works like a short rehearsal that tells muscles when to move, so hand and ball meet at the right spot. Researchers who study movement have shown that the nervous system builds and uses internal models to plan and correct actions in ways that match what you see when athletes practice and when ordinary people reach for a cup. These internal models do not need a perfect picture. They need a good enough guess, and that is often all the brain can manage while still being fast. Prediction works at many layers. At the lowest layer, the brain guesses where a single finger will be in the next heartbeat of time. One layer up, it guesses the next sound in a sentence and the next note in a tune. At a still higher layer, it guesses whether your day will be calm or busy. This hierarchy means that small errors shape immediate moves, while bigger errors shape what you expect in life. Learning happens when the brain uses prediction errors to adjust models across these levels. Neuromodulators and chemical messengers in the brain help mark which errors are worth paying attention to. That way, the brain learns faster from surprises that matter and ignores those that do not. The chemical called dopamine plays a special role in this teaching work. Long-running studies of how animals learn have shown that dopamine cells in certain brain areas signal a reward prediction error. When an outcome is better than expected, these cells fire in a way that tells the brain to remember and repeat the action that led to the surprise. When an outcome is worse, the signal changes and the brain learns to avoid that action. This simple-looking rule helps explain how habits form, how we learn to expect rewards, and how attention shifts when something important happens. In short, dopamine helps the brain tune its predictions in ways that are useful for living. When the brain's predictions fit the world, things are smooth and the present feels immediate. When they fail, the gap shows itself in many ways. Sometimes the mind creates false perceptions when prediction wins out too strongly over sensory input. In conditions such as some forms of psychosis, the normal balance between expectation and the incoming signal can be broken, and this may help explain why people perceive things that others do not. Careful scientific work has linked such symptoms to problems in predictive coding and in the way the brain assigns confidence to its guesses. This view does not reduce complex human experience to a single cause, but it gives a powerful way to think about why the mind can sometimes trust its own story too much. Other failures are softer and common. The strange sense of having been somewhere before, called déjà vu, can come from a short mismatch between prediction and the raw signal the brain receives, creating a false feeling of familiarity. Optical illusions work because the brain's expectations push perception away from the raw input and toward a simpler or more likely interpretation. In sudden danger, people often report that time seemed to slow down. One reason for that report is that when the brain faces a life-threatening surprise, it shifts its balance toward detailed analysis and stores many rich details in memory. The richness of those memories can make the event seem longer when it is recalled. In each case, the common thread is that our sense of time and reality depends on the dance between what we expect and what we actually get. The brain also uses prediction to live with other people. Mirror neurons discovered in studies of primates and discussed widely in human research seem to fire both when we act and when we observe others acting. These neurons and the networks around them help the brain simulate the likely next moves of another person. That is why two people who know each other well can finish each other's sentences, why musicians fall into a shared rhythm, and why a friend can guess your mood from a small change in your face. Social prediction is not magic. It is a finely tuned use of models that help us read and anticipate other minds. This social time machine is both useful and fragile. When it fails, we can misunderstand others or feel awkward in a group. Prediction is not perfect, and it is not solitary. It is a communal skill built through practice, sleep, and the gentle feedback of life. Musicians and athletes get better because practice sharpens the models and reduces costly errors. Sleep helps by replaying and consolidating patterns so that the brain's models are tuned overnight. Simple tools like a timer or a checklist aid the brain by offloading part of the guessing. In difficult cases, medicine and therapy can help rebalance the trade between expectation and sensory truth, giving space for better learning and calmer life. The picture the science gives is not cold or reducing. It is a warm, human story. Your mind is constantly making bets in the next moment, so your hand meets a cup, so speech keeps flowing, and so a conversation arrives where you expect it. Sometimes the guesses are right, and the world feels seamless. Sometimes the guesses slip, and the mind must learn. Either way, the brain's prediction machine is the quiet craftsman behind the ordinary miracle of living in time. Close your eyes for a moment and picture a slow afternoon when you had time to sit and think. Now imagine that same afternoon stretched and folded by a dozen small tricks your brain plays without asking. You plan, you postpone, you reach for small pleasures, and the days go by. None of this feels wrong in the moment, yet the way you feel time, value the future, and respond to small and large risks is shaped by ancient wiring and modern temptations. The result is a life lived with broken intuitions about time. A life where the very machines inside your head that helped your ancestors survive can now steer you away from the decisions that would help you and your world the most. One deep reason why we make poor long-term choices is that our minds treat future rewards as if they were worth much less than immediate ones. Scientists call this temporal discounting, and it shows up in many ways. When the harm or benefit is far ahead, we tend to treat it as distant and optional, even when it will matter a great deal. This is one reason why responding to slow-moving problems like climate change is so hard for individuals and whole nations. The tools of economics and psychology explain why people prefer smaller immediate gains over larger distant ones, and why policies that rely on individual foresight alone often fail. The research is clear that human time preferences and the way we discount future payoffs help explain weak public response to long-term environmental risk. A sibling of that trouble is how our minds misunderstand compound change. People are prone to what researchers call exponential growth bias. We tend to think in straight lines when the world bends in curves. This makes it hard to see how debt grows, how interest compounds, or how an infection multiplies until it suddenly seems everywhere. Financial errors follow from this bias. Many households underestimate the future cost of loans or the power of steady saving, and those misjudgments are linked to real-world outcomes like borrowing more and saving less. The math of compounding is simple, but our intuition misreads it. That mismatch between what our minds expect and how numbers behave leads to quiet, costly mistakes in money and in public policy. Health decisions come from the same fold of time thinking. Choosing a cigarette now or dessert instead of a long-term diet plan makes sense when the reward is immediate and the cost is delayed. Studies show that people who heavily favor immediate rewards over delayed ones are more likely to relapse into addictive behavior and to make other choices that hurt long-term health. The measure researchers use to capture this pattern, called delay discounting, predicts a range of habits from overeating to missed medical care. Understanding that this pattern is common helps shift blame away from willpower alone and toward designing better supports and environments that make healthy choices easier. Into this fragile psychology steps an industry that knows how to feed it. Modern digital platforms are designed around unpredictable rewards and quick hits. The same psychological rules that make a slot machine hard to ignore help a social feed keep pulling your attention back. Computational studies show that likes, comments, and shares function as social rewards that models of reinforcement learning capture neatly. Neuroscience tells us that dopamine systems, which evolved to signal learning about rewards, respond to surprising or variable outcomes. When you scroll, you are riding a stream built on variability and surprise. That makes it easier to check again and again for small social feedback and harder to step away. The business model of many apps depends exactly on this tug, and that tug rearranges your sense of time by privileging immediate social reward over longer-term plans. There is a hidden cost to all this constant grabbing for the next small hit. Human thinking is not built to bounce from one interruption to the next without tax. There is a warm, quiet grace in admitting a limit. It is small wonder that our minds feel confident about the things we touch and see. They were built to notice faces, to follow a running deer, to tell day from night, to plan a hunt and raise a child. They were not built to make sense of the strange rules that govern atoms, or to feel the stretching of time near a black hole. That does not mean our minds are broken. It means they are beautifully tuned to the human world, and science gives us tools and ideas to step past those limits when we want to learn more. The basic science of how the brain makes time shows that perception is a construction that stitches past moments together into a flowing now, and that gentle craft is what lets life feel steady. Knowing that the present is made helps us live with the fact that we do not experience reality raw. Our brain borrows information from what happened just seconds ago to keep things from jittering, and it uses patterns to smooth motion and faces so life looks calm. This continuity is useful and kind, but it also creates a blind spot. When a problem unfolds slowly, or when a pattern grows unseen by tiny steps, the mind may not sound an alarm because the world still looks steady. Scientists who study perception call these effects serial dependence and continuity fields, and they show how the brain makes the ongoing story you feel. Once you see that your now is partly a stitched past, you can learn how to work with that stitch rather than be surprised by it. Acceptance of limits is not the same as giving up. It is the first step toward using better tools. Mindfulness and simple attention practices are among the softest and truest tools we have. Quiet practice trains the parts of the brain that hold attention and notice detail. People who learn to sit and breathe with attention tend to become steadier in the face of distraction and more able to feel the flow of experience without being swept away. Many studies show that mindfulness changes brain networks tied to attention and sensory awareness, and it can change how people sense duration and presence. The practice does not make you able to see the atom or to feel relativity, but it does make your felt present cleaner and your choices less driven by sudden urges. Beyond attention, we have other practical ways to turn our time machine into an ally. One surprisingly powerful skill is the deliberate act of imagining the future. When people vividly picture a future scene of themselves saving money, quitting a bad habit, or finishing a project, they often act more like their imagined future self. Psychologists call this episodic future thinking, and research shows it can reduce the temptation to choose small, immediate rewards over larger, delayed ones. The mind that can replay past moments can also recombine those memories to simulate plausible futures, and those simulations make long-range choices feel more real and more urgent. Using this kind of mental rehearsal is a simple, evidence-based way to make the future feel less distant and to nudge behavior toward long-term aims. We also have the humble power of tools: a calendar, an alarm, a saved automatic transfer to a retirement account, a rule that turns off notifications after dinner. These are not clever tech tricks. They are ways to move some of the work of holding the future out of fallible attention and into the steady world of objects and habits. Engineers and psychologists call this external scaffolding. It is how people make choices that their raw feelings would not have made easy. Visualization, as when you write a clear plan and picture the step-by-step scene, works like a compact rehearsal. The more concrete the image, the more the brain treats the future as a real place to return to when temptation comes. The science of perspection shows that practice plus simple tools can change behavior in measurable ways. There is no single magic cure. The work of living wisely with a past-seeing brain is small and steady. It often begins with habits you can practice. Turn a decision into a default. Put your phone out of reach when you need deep time. Spend a few minutes each evening imagining how tomorrow should go, with sensory detail, names, and steps. Make saving automatic so that your future self benefits without daily willpower. These are practical moves that use the mind's natural powers and the world as steady props together. They are not about forcing the brain to be other than it is. They are strategies that respect the brain's shape and give it a better road to travel. Research on simple interventions and on routines supports these modest but effective tactics. There is a spiritual tenderness to this science too. When you learn that your brain assembles moments into a present, you can feel both awe and humility. Every scene you live through is a delicate act of binding, a miracle of timing, prediction, and correction. Consciousness arises from the brain as slow, noisy signals being woven into a smooth story. That story is not less true for being constructed. It is the human way to have a life that feels continuous and warm. The same machinery that sometimes makes us short-sighted also makes love possible, music shared, and stories told. That double edge is part of the beauty of being human. Finally, remember that the future is not fixed because your perception lags. The fact that you live inside stitched pasts does not make life a playback of a set script. Prediction, practice, and choice bend the path forward. When you use attention, imagination, and simple tools, you change what comes next. Science gives you ways to see the edges of your own time machine and to steer it. The world is larger and stranger than our senses first let us know. That truth can make you feel small, but it can also make your life richer. When you next look at the sky, feel the old light and the craft of your own mind at once. Let awe meet action, and let the gentle work of attention and planning be the way you live wisely with the beautiful, imperfect time machine that is your brain.